All right. I think, given what I said last time, it might be worth me just doing another example to death, introducing this idea of multiple charges and holding off on doing dipoles until the next time. This is a hard concept, but I think we're still getting hung up on some of the vector stuff, which is then making it harder for us to then get on board with the concept of this electric field. So let's recap the main ideas. Last time we talked about the electric field of a single point charge. That this is a way for this charge here to make itself known throughout the cosmos, and that it sends a signal out that alerts any other charges of its presence. This essentially is a way that this charge here in the center allows other charges to be aware that there is a charge there and that they should feel a force as a result of there being this positive charge. The convention, which we motivated last time, is that the electric field, this signal, this electric field, points away from positive charges and towards negative charges. So I have, again, two drawings from the textbook here of what this electric field might look like around a single positive charge and around a single negative charge. The closer you are to the charge, the stronger the electric field. Note by the length of the vectors. That is because of the inverse square component of the electric field, and then it also depends on the charge itself, which can change the length of the vectors as well. So, the electric field, again, formulaically, or the formula for it is given by this here. Looks very much like the Coulomb force, but we've divided away that Q, so that this electric field is talking about the electric field that is created by this Q. This Q does not feel a force because of this electric field. This Q creates an electric field. So if this is Q, then this electric field that we're seeing here is given by this formula. So then if I had some other charge, maybe capital Q, located somewhere else, that capital Q would feel a force from little q because of the electric field. We would have to find that the electric field at that point might be something like that. And then I would be able to use that to figure out the force that capital Q is feeling from little q. And I think there was some confusion last time about this, that this electric field, which originates from little q, does not need a second force to exist. This exists solely because of little q. I could have this single charge, and that could be the only positive charge in the universe. And there would be an electric field that it creates all around it, like what's drawn. So, to go over the terms that are in the formula, right? K, Coulomb's constant. Q is the magnitude of the charge. Here we are not doing the absolute value because we are allowing that if Q is negative, we're allowing that negative to actually do some work this time. And this is what allows us to be able to kind of conveniently write so that positive charges point away and negative charges point towards. There's no absolute value here, notice. Then it's divided by the square of the distance. Distance to what? This r vector is the distance from the charge to some point of interest. I'm gonna, before I was kind of writing r with a little kind of empty spot. Here instead I'll write POI for point of interest, right? This is some location away from the charge that you're just curious of what the electric field looks like there. So I could have some point, here. What does the electric field look like there from this charge, right? And I could figure that out with this formula. So this vector here is, again, if I want to think of it in terms of vectors, since it's to this from this is a vector that points from the charge Q to this point of interest, such that then the magnitude of that vector is nothing more than the distance from the point of interest, or to the point of interest from Q. So again, just to reiterate, this point of interest here can be anywhere you want. There does not have to be a charge located at that point of interest. I can still talk about the electric field at that point. Because again, this particular charge creates an electric field everywhere in the universe. And if I want to know what the electric field looks like here, then that's my point of interest. And then I have to figure out what's the distance between this charge and my point of interest. If my point of interest is all the way over here, then I have to figure out, if that's POI, then I have to figure out the distance between it and my charge Q, and that's R. So again, this point of interest can be anywhere you want. There doesn't have to be a charge there. If there is a charge there, then we can also calculate the force that charge feels. But again, we're now focusing on just the electric field that this Q creates. So again, I think maybe it's worth just doing another example of this, because the vector stuff should not be kind of throwing us off. So let me do a problem where I have some charge Q, which is negative 10 nanocoulombs. And just by that alone, I could say nothing else. I then know I could ask conceptually what, is there an electric field? Of course there is an electric field. That charge Q of negative 10 nanocoulombs creates an electric field everywhere around it, and that electric field is going to point towards that charge, such, and the magnitude of these arrows will decrease as I get farther away because of that inverse square distance, and it depends on the formula that's given above. It depends on the amount of Q, 10 nanocoulombs, as well as the distance away from it. And now suppose I'm curious to know what is the electric field at this point here, which happens to be negative 3 centimeters to the left and 4 centimeters above. And then the question is, what is the vector E at this point? So negative 3 centimeters, comma 4 centimeters. Or again, if you like columns, negative 3 centimeters, 4 centimeters as a column. And again, notice I did not say that there's a charge there. There doesn't have to be a charge there. There's still an electric field there. Again, if there were a charge there, then I could calculate the force that charge feels. And I could use the electric field to do that. I should have wrote that up here, right? So, the force that, say, capital Q feels from little q is then the charge, capital Q, multiplied by the electric field that results from little q. The big charge Q, or capital Q, feels a force depending on what the electric field from the other charge is. But we're not going to worry about forces. Let me move this away from all that. So, what is the electric field at that point? Now again, there's many ways you can figure this out. That's the great thing about physics. There's often multiple ways, or science in general, there's often multiple ways to solve a problem. And we can do it so I'll try to do it in multiple ways. So, first thing I could ask, first thing I want to always do is think conceptually. This is a negative charge Q, so I know that the electric field is going to point towards Q. So that, whatever E is, I know it should point in that direction, towards little q. So geometrically, that negative 3 and positive 4 is going to play an important role in determining the direction that E points. Let's first start with the magnitude. What is the magnitude of E at that point? Well, based on the formula, that is just K Q over R squared. And here I did put the absolute value back because magnitudes are always positive. The length of a vector is always positive. So again, what is this? What are these symbols? K is a constant. Q is the magnitude of the charge creating the electric field. Or I could write E sub q, right, for all of these, right, because it's the electric field created by little q. And then r is the distance between the charge and the point of interest. So I could ask, what is the distance between Q and this point of interest? Well, just geometrically, you should hopefully start to see a triangle. One side of the triangle is length 3 centimeters. The other length of the triangle is 4 centimeters, where Q is here and the point of interest was there. So if I want to talk about the distance between them, then Pythagoras provides us a way. Looks like that's just 3 squared plus 4 squared. And those were have units of centimeters. So it looks like then that's just square root of 25 centimeters, or 5 centimeters. Now then you might say, what about, why was it negative 3? Well, 2 reasons, I guess, right? I'm going to square it, so whether it was negative 3 or positive 3 doesn't matter really anyway. And I'm looking at this in terms of a triangle, right? I'm looking at this in terms of this triangle, and triangles always have positive lengths, right? There's no negatives in a triangle. And this is just the length of one side, the length of one side, and the length of the hypotenuse. And the fact that it's, negative 3 on the left, by the coordinate axis, has no real relevance when it's just a geometric triangle. One length is just 3 centimeters. The other length is 4 centimeters. And if I want to be super, really I should say that this is 3 centimeters squared plus 4 centimeters squared. And then when I square it, that is 9 centimeters squared plus 16 centimeters squared. But then that is square root of 25 centimeters squared. And then that's the same thing as 25 under the square root times the square root of centimeters squared, which of course then is just 5 centimeters. Again, I'm hoping that these things are becoming a little bit more second nature. So the distance between the charge and this point of interest is 5 centimeters. So if I want to then figure out the magnitude of E, then looks like it's going to be K, the magnitude of Q, divided by the square of this distance between them. So it looks like it's 9.10 to the 9. I'm going to make sure before I plug in any numbers, I'm always writing them in terms of SI units. So 10 nanocoulombs, nano is 10 to the minus 9, 10 times 10 to the minus 9 is 10 to the minus 8 coulombs. And then centimeters is not the SI unit, so that's going to be 5 times 10 to the 2, negative 2, and that's going to be squared. Then I won't bother writing units because I've used their values in SI units everywhere, so I know that at the end of the day it will be whatever the SI unit is. So it looks like then it's 9 times 10 to the 9 times 10 to the minus 8 all over 25 times 10 to the minus 4. I can combine the exponents. It looks like it's 9 times 10 to the 9. I could bring the, I'll just write it out explicitly then. I can bring the 10 to the minus 4 upstairs. So it looks like I have 9 plus 4 minus 8. So it looks like it's 9, 10 to the 5, all over 25. And I could whip out a calculator at this point, but I could also just, intuitively, like, what is this number kind of just essentially close to? If I were to approximate this, what is it close to? If I whip out the calculator, I get 3.6 times 10 to the 4. Fine. But 9 is essentially 10. So I'll write, this is approximately 10 times 10 to the 5 divided by 25. Now I can't, 10 divided by 25, isn't a clean division. But if I yank out one of those 10s, this is the same thing as 100 times 10 to the 4 divided by 25. 100 divided by 25, that's easy, that's just 4. So this is approximately 4 times 10 to the 4. Then nano newtons per coulomb. The real answer is 3.6 times 10 to the 4 newtons per coulomb. But again, if I can avoid blindly punching in things in a calculator, because then my brain shuts off, I prefer that. I'd rather do, like in this case, I approximated. And so I was mentally involved the entire time. And so I'll use the 4 times 10 to the 4 in future calculations, since it's a little cleaner. But here, all we did was just plug things into the formula for the magnitude of the electric field. Now we have to ask, what about the direction in this case? Well, if I want to just think geometrically, which is a perfectly fine way to do things, there's Q, there's my point of interest. Then I know that this is 4, this is -3. If I want to describe the direction, I might describe it by an angle. So, of course, I should always look for triangles, and lo and behold, there is a triangle there. Now I know the electric field is going to point in this direction. And this 3 and the 4, those are just lengths. So they don't necessarily have anything to do with the electric field, I guess, based in terms of, they played a role in that we needed the inverse square of the distance. That's where the 3 and the 4 played a role. But this also determines the direction. Based on the direction, I know that this arrow must point towards the origin, right? Because the electric field must point towards the charge. So this -3 and the 4 also tells me about what direction the electric field must point in. So if I want to describe this angle theta, then again, I just have a triangle, particularly a right triangle, where this is 3, this is 4, and this is 5. Nice 3, 4, 5 triangle. In which case then I could say, okay, well then cosine of theta, the swoosh touches the 3, so that's the adjacent 3 over 5. So cosine of that angle then is 3/5. Or, in that case then, theta, here I do need a calculator, theta then, when I figure it out, is about 53.13 degrees. So I could say that the electric field is about 4 times 10 to the 4 newtons per coulomb, and points in what direction? Well, this angle is telling me, I can't say it points 53 degrees clockwise from the negative x direction, because the electric field is pointing kind of this way as a result. Oops. But I could probably geometrically figure out what's going on, because I know, let me redraw the axes. I know if it's pointing towards Q, let me use the dotted line. I know if it's pointing towards Q, so that looks kind of, not dotted, no, I don't want dotted, like this. And we just said that this angle here was theta. Well, then I know that this angle here is theta. So then it looks like I have an electric field that is pointing kind of that way, and then relative to the axes, it makes this angle with the axes. So I could say that the electric field has a magnitude of 4 times 10 to the 4 newtons per coulomb, and it points in a direction of 53.13 degrees, kind of clockwise from the x hat direction, right, the positive x direction. That's one way you can write. I've given a magnitude and a direction. Is that the only angle you could have used? Of course not. So if I redraw everything here, right, here was Q, here's my point of interest. There's my hypotenuse, where we know this is -3, this is 4, this is 5. I could maybe describe things by maybe this angle, call it phi. And I know the electric field, again, is pointing towards Q. So I could ask, what is that phi angle? Could I describe the electric field that way? Well, then it looks like the triangle looks something like this, where this is phi, this is still 5, this is still 3, this is 4. But then notice it seems like cosine of phi is 4 over 5. And the swoosh touches the 4, so that's the adjacent, or divided by the hypotenuse. So then, in this case, phi should be, and I'd say stop. You should be able to say 2 different ways that you could figure out this angle. One of them you could probably do in your head. The other requires a calculator. Of course, you could pick up the calculator and do the inverse cosine of this angle, and you would get 36.87 degrees. But of course, based on what you calculated for theta up above, that better be the same thing as 90 divided by, or 90 minus 53.13 degrees, which of course it is, because those 2 angles better add up to 90 degrees based on what I've drawn. So, in this case then, how could I describe this? So I have, let me redraw the axes again. Then I have my electric field. That's supposed to be red, oh well. So I have my electric field that's kind of pointing in this direction. And I've just calculated this angle phi, which then, by geometry, looks like that's the same as this angle. So then I could say that E is 4 times 10 to the 4 newtons per coulomb, and it points 36.87 degrees counterclockwise from the negative y direction. That's how I've defined phi here. If I start here and I go counterclockwise that way, that defines phi the way I've drawn it. That would then tell me how E is pointing. And it's of course identical to what I did up above. This is geometry. Now if I want the components, then how about we use phi? So I had my electric field vector is pointing this way. Note I'm putting it at the origin. Is that okay? Of course, because vectors are independent of coordinate axes. I'm just drawing it so that I have something that is easy for me to visualize. And that was theta, as we defined it before. So then if I want to get the components, then again, look for those goddamn triangles. Seems like in this case then, there is the x component points to the right, and then the y component points down. So then I expect the x component to be positive, the y component to be negative. Move this out of the way. There we go. So then, again, it's just a triangle. Here I have the magnitude of E as the hypotenuse. Then we have this is EX, this is EY, and here is my angle, theta. Again, the swoosh touches e to the x, so then that looks like e to the x is the magnitude of E times cosine. In that case, and then e to the y is the magnitude times sine, but I'm going to throw a negative sign in based on the way I've drawn it because I know that it's going to have to point down. That's why I always like to draw triangles, because then my angles are always kind of between 0 and 90 degrees. So then cosine and sine are always going to be positive when the angle is between 0 and 90 degrees. And then I can manually put the negative sign in based on the drawing. So then you get the components, which I believe in this case is about 2.4 times 10 to the 4. And the y direction, 3.2 times 10 to the 4 with that negative sign, because it's going to point down. Could I have done this using phi? Of course. I would get something different. Sorry, well, I would get the same components. But it must get the same components. But let me just draw it out and do it explicitly. So again, here's my e. Then I've defined this to be phi. So then the triangle looks like it's this. Okay, I'm not sure how you thought that was going to be a square. Phi, that looks like this is e sub y. This is the magnitude of e. And this is e sub x. But then notice the swoosh touches e sub y. So then it's e sub y in this case is the magnitude of e times cosine of phi. I'll throw in that negative sign because it looks like it's pointing down. And e sub x is the magnitude of e times sine of phi. So again, I've said this already, I'll say it again. Don't assume cosine is always x, sine is always y. Draw a frickin' triangle. In this case, the way the triangle is drawn, x is sine and y is cosine. And of course, when you plug in the values, you should get the same thing, the same numbers. So that seems like we've been able to write that, we can write that the magnitude of E is 4 times 10 to the 4 newtons per coulomb, in the, pointing what was theta again? 53. Pointing 53.13 degrees clockwise from the positive x direction. Or we could write it as that the vector E is, we said it was 2.4 newtons per coulomb in the x direction, and negative 3.2 times 10 to the 4 newtons per coulomb in the y direction, with that negative sign because it points to the right and down. All right, that is one way we could have figured out, from the original problem of what is the vector E at this point. Right, we had a magnitude, and then we figured out the direction, and then given the magnitude and the direction, did some triangle stuff and broke it up into components. If we wanted to do it the way that was kind of introduced in lecture, which is the more explicit way, I think the cleaner way, once you kind of get a feel for this, go to a new page and redraw. Here's Q. Here's my point of interest. Negative 3 centimeters, 4 centimeters. Negative 10 nanocoulombs. The electric field, we know, will point towards Q. So in this case, again, I wrote E is K, Q, magnitude of the distance between them squared times r hat, where r is kind of the position of the point of interest minus the position of the charge Q. Well, then we just got to figure out what these vectors are, mostly. So the point of interest looks like it's located at negative 3 centimeters, comma, 4 centimeters. or if you want columns, -3, 4 centimeters. The position of the charge is conveniently at the origin. At this point, the stupid screen broke again, and I did not realize for like 10 minutes. So, again, sorry for the jump. So, in this case, then, we can figure out this position vector. Real nice, because the charge is at the origin. Looks like in this case, it's then just -3, 4 centimeters. The magnitude of this vector is then just, again, 5 centimeters. And then the unit vector, which is 1 divided by this magnitude, so 1 divided by 5 centimeters, multiplied by 3 centimeters, 4 centimeters, multiplied by the original vector. Note the units cancel, and this becomes a vector that looks like it's -3 over 5, and then 4 over 5. Why is it dimensionless? Again, but this is supposed to be just the direction, right? It doesn't matter whether it's 4 centimeters or 4 meters, right? The fact that it's, over 3 and down 4. Or actually, sorry, in this case, it's to the left 3 and up 4. Is what dictates this. This is just telling you the direction. The magnitude is then given by, that has the unit in it. So we could ask, does the direction make sense? Looks like this is pointing to the left and up. And this is supposed to be a vector that points to the point of interest from the charge. So it looks like, indeed, I have to go left and up to get here. So seems like it's pointing in the right direction. And then I can put this all together. So then E is then just K, Q over the magnitudes squared times R hat. And if we think of what we did earlier, the thing I wrote in parentheses, we already figured out that that's going to be 4 times 10 to the 4 newtons per coulomb. But now I'm going to add that negative sign because it's not the absolute value of Q, it's just Q. So there's that, given that it's a negative charge, I have a negative sign. And that's multiplied by the vector 3/5, 4/5, which when you multiply them all out, unsurprisingly, you will get the same values as before. In the x direction, note the negatives cancel. 2.2 times 10 to the 4 newtons per coulomb. 2.4. And then negative 3.2 times 10 to the 4 newtons per coulomb in the y direction. So you get the same exact answer. Again, unsurprising. You better get the same exact answer, but this is just being done in a different way. This essentially is doing it the vector way, where you're just thinking of it in terms of vectors. But again, conceptually, all this is saying is that you need to know the distance between the charge and the point of interest. That's R. And then this way is probably the way you were more familiar with, right? If I know kind of geometrically how things are pointing, I can then figure out the components. If I can figure out angles and magnitudes, I can do it that way. Which of course is going to give you the same answer as what we did here, but notice here I was able to do it more or less in 3 lines compared to some of these methods. But again, both are equivalent. Both have use depending on the problem you're doing. And depending on what you're doing, it might be more advantageous to use one method over the other, which is why I don't just do it this way in this class, because I assume you've seen it this way before, but doing it kind of this way gives you yet another kind of tool in your toolbox once you get comfortable doing it. All right, so again, that's all sort of stuff should become a little bit more second nature, so that it doesn't distract from the concepts. Let me introduce the idea of multiple charges. I'll be brief because I don't think anything about this is too shocking. Suppose now I have multiple charges, Q1, Q2, Q3, and I have some point of interest. But I ask myself, what is the electric field at that location? Everything up to this point, we've just been using a single charge. But now we have 3 charges. So presumably each of those charges are creating their own electric fields. And let's suppose Q1 is a positive charge, so we know that that electric field is pointing away. Suppose Q2 is negative, so then that electric field is kind of pointing towards. Then Q3, maybe it's also positive, it's kind of pointing away. And so what's going on at that point of interest? Well, if I think just individually, if it was just Q sub 1, then I know that it's going to create an electric field that points away from Q sub 1. If it's just Q sub 2, I know that it's going to create an electric field that points towards Q sub 2. And if it was just Q sub 3, I know there's going to be some electric field from just Q sub 3. You might ask, is the net electric field just the sum of these? And indeed, it is. But we can motivate why that should be the case. Essentially, we're saying that E obeys the superposition principle. That I can superposition principle. That E net is just the sum of the individual E's. If I have multiple charges going on, I just figure out the electric fields from each of those individual charges at that point of interest and add them up. Now, why might we think that should be the case? Right? I should be able to prove this in some way versus just declare. Essentially this results from, given that forces obey the superposition principle, forces obey superposition, this result follows. And again, let me motivate it briefly. And then I might just end it there, or maybe I'll do one quick example. So, suppose I were to put a little charge there. So at this point of interest, let me just redraw the picture. So we have Q sub 1, Q sub 2, Q sub 3. Suppose I were to put a little charge here, right? A test charge, delta Q. The idea of a test charge is that it's something that is so small that it's not going to really impact what's going on everywhere else. You can imagine if I put a giant honking charge there, it's going to want to attract or repel Q1, Q2, and Q3 in such a way that the configuration is going to change very quickly. Essentially, this hypothetical test charge is that it's something so small that we can measure the forces on it, but it itself is not going to kind of disrupt the system. Sometimes I find that idea more confusing than helpful. So if that didn't really help, ignore everything I just said. So I could ask, if there's a little charge delta Q at that location, then what is F net, on kind of this delta Q? Well, the net charge on delta Q, of course, is then just going to be the charge on delta Q from Q1 plus, the force on delta Q from Q2 plus the force on delta Q from Q3. Not too surprising. And so I won't write it out. I'll just write one of them out. So it's going to be kind of K delta Q, Q1 divided by the distance between delta Q and Q1 squared, along the direction, between them, plus, et cetera, et cetera. And there'll be a Coulomb term for delta Q and Q2, then a Coulomb term for delta Q and Q3. But then since we defined the electric field at that point of interest as the force divided by delta Q, again, essentially extracting the delta Q out so that we're thinking about just what's going on as a result of all the other charges that then are creating this force that delta Q feels. Then you can look at the definition in the previous lecture and see that that just then becomes the electric field of Q1 plus the electric field of Q2 plus the electric field of Q3, at the point of interest. So they obey a superposition principle as well. Let me just sketch out one quick example and call it. And suppose I have a square, and maybe I'll leave the math part of this for you as practice. So I have a square, each side of length r, and here there's a positive charge, plus E. Here there's use different colors. Here there's a negative charge, negative E. And then at the top right is another charge of plus E. And I would like to know, what is the electric field at the other corner of this square? So first thing I would do is, of course, think conceptually what's going on. The lower left charge is a positive charge, so the electric field I know points away in that case. So I know that that electric field is going to point, looks like, in the positive x direction. For the top right charge, it's also positive, so I expect that electric field to point down. And then for the negative charge in the opposite corner, I know that it's going to point diagonally up and to the left. So in this case, I expect that the net electric field is probably going to be the sum of these three vectors. And here I would suggest putting the origin at your point of interest and then actually calculating what these vectors are individually first. And I'm just going to write down the answers. So the electric field of the lower left charge is just K E over R squared, and it's pointing in the positive x direction. The electric field in the upper right is going to then be negative K E over R squared in the y direction. So the negative then makes it point down. And then the charge that is in the diagonal corner, right, it is not a distance r away, but is the distance square root of 2 times r away. Because again, triangle, that's r, and that's root 2r. So its distance is not r, so I better not divide by r squared, but instead I'm going to divide by root 2 over r squared. The charge is the same, right? K is the same. And then I need the direction that is going to point in the right direction. It looks like it's pointing left and up. And given that it's a square, right, I know that both of these better be the same. So it's going to end up being 1 over root 2 and then plus 1 over root 2. And again, you should be able to figure that out on your own of why that is the direction vector r hat that points to the upper left from, well, sorry, I guess it points, let me actually pull the negative out because it's a negative E, so that's where the negative is coming from. So I do this and this. Right, so this vector here, right, remember, is supposed to point to the point of interest from the negative E in the upper left. And indeed, it looks like it points to the right and down, which is what I would expect. But then since the charge in that corner was a negative E. Let me write this as K times negative E. That negative E then flips the sign so that then this ultimately points, KE over square root of 2 squared is 2. Then you have R squared. Then it looks like this is negative 1 over root 2 plus 1 over root 2 if I take the negative inside. So the electric field points left and up, which is what we expected it to be. So then, given once you have all those, E net at your point of interest is just the sum of them. So I just add them all together. So if I do them as columns, right, I have KE over R squared. And the first vector was only in the x direction. The second one was KE over R squared, only in the y direction. Note the negative is out front, which is what makes it point down. And then I have plus KE over 2R squared. Then I could even factor out that kind of 1 over square root of 2. So I'll have a square root of 2 in the denominator as well. And it looks like that is negative 1, positive 1 in that case. And then, unfortunately, all the denominators are not the same, but then we just have to simplify. So if I combine the first two, looks like that becomes KE over R squared. Looks like I have 1 minus 1. And then I still have the plus KE over, looks like it's 2 root 2 R squared negative 1, 1. Which I could add together. I could just leave it as is. Or I could write this as, it's going to be a big messy column. KE over R squared minus KE over 2 root 2 R squared in the x direction. And then, let's see, it looks like then it's negative KE over R squared plus KE over 2 root 2 R squared in the y direction. Or put some dots, not that it's a fraction, but that the x component and the y component. Though I would hope that you could simplify this more and write this with with the same common denominator. In which case I think it becomes something like KE parenthesis 2 root 2 minus 1 close parenthesis all over 2R squared. And then if you want a direction vector, 1 over root 2, negative 1 over root 2. That's just math. Again, so there I skipped over the math entirely, right, for you to practice. Hint of what you might try to do with, with this vector. Think of it, what if the problem was only this? Could I figure out the electric field at this location from this charge? Then similarly, what if this was the only problem? Could you figure out that this was the electric field from this charge at this location? And similarly, if this was the only problem, this was the entire problem, could you figure out that this was the electric field that results? If you can do that, then when you have multiple charges, you just add them together. And then that's just math. All right. Screen did not break that time, so there we go.